Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video we are reading amines. Introduction. Amines are the organic derivatives of ammonia in which one, two or all the three hydrogen atoms have been replaced by alkyl, aryl or ara-alkyl groups. For example, ammonia, methylamine, dimethylamine, triethylamine. Amines form an important class of organic compounds since they not only serve as starting materials for the synthesis of other classes of organic compounds but many of them also possesses profound physiological activity. In this unit we shall briefly discuss the chemistry of aliphatic and aromatic amines. Classification of amines. Amines are classified as primary, secondary, and tertiary according as when two or all the three hydrogen atoms of ammonia are replaced by alkyl or aryl or ara-alkyl groups as described below. Primary amines. Primary amines are the derivatives of ammonia in which one hydrogen atom of ammonia has been replaced by alkyl, aryl, or ara-alkyl group. Therefore, their functional group is the amino group NH2 depending upon whether the group directly attached to the nitrogen atom as an alkyl, aryl, or ara-alkyl group. They are called aliphatic amines or alkyl amines, aromatic amines or aryl amines, and ara-alkyl amines respectively. For example, methylamine, aniline, benzylamine, amine. Secondary amines. These are the derivatives of ammonia in which two hydrogen atoms of ammonia have been replaced by alkyl, aryl, or ara-alkyl groups. Therefore, their functional groups in the amino group. It may be noted here that the terms primary, secondary, and tertiary use have been different meanings than those used in case of alcohols. In alcohols, primary, secondary, and tertiary alcohols refer to the type of the carbon to which OH is attached. Thus, 2-propan-amine is a primary amine, but 2-propanol is a secondary alcohol. Depending upon whether the two groups attached to the N atom are same or different, secondary amines are further classified as simple or mixed. Further, the secondary amines may be purely aliphatic or purely aromatic or mixed aliphatic aromatic depending upon the nature of the two groups attached to the nitrogen atom. For example, dimethylamine, ethylmethylamine, diphenylamine, and methylaniline. Tertiary amines. These are the ammonia derivatives in which all the three hydrogen atoms of ammonia have been replaced by alkyl, aryl, or ara-alkyl groups. Therefore, they contain tertiary nitrogen as the functional group. Like secondary amines, they may also be purely aliphatic, purely aromatic, or mixed aliphatic aromatic. For example, trimethylamine, ethyl dimethylamine, and N-dimethyl-aniline. Quaternary ammonia compounds or salts. Apart from three types of amines, there is another class of compounds called quaternary ammonium salts. These compounds may be regarded as derivatives of ammonium salts in which all the four H atoms of the ammonia ion have been replaced by alkyl or aryl or ara-alkyl groups. Ammonium salt, quaternary ammonium salt, tetramethylammonium iodide, tetraethylammonium hydroxide. Structure of amines. The structure of amines is similar to that of ammonia, like in ammonia. N of amines is also sp3 hybridized. Three of the sp3 orbitals, which contain one electron, each form sigma bonds either with H atoms or the alkyl or aryl groups, while the fourth one contains a lone pair of electrons. For example, the structure of trimethylamine is shown below. Since lone pair bond pair repulsions are much greater than bond pair pair repulsions, therefore the bond angles between any two adjacent H atoms or alkyl groups decreases from the tetrahedral angle of 109.28 to 107 in primary and secondary amines. However, in case of tertiary amines, due to steric hindrance between the three bulky alkyl groups, the bond angle increases from 107 in ammonia to 108 in trimethylamine. Thus, all the three amines, like NH3, have pyramidal shape. Stereochemistry of amines. A tertiary amine like NH3 has a pyramidal shape with its lone pair of electrons present in a sp3 orbital. If this orbital containing the lone pair of electrons is considered as the four different substituent, then the tertiary amines of the type R1, R2, R3 and because of their pyramidal shape should be chiral and hence resolvable. But in actual practice, such type of tertiary amines have never been resolved. This is due to the reason that the energy difference between the enantiomers of such type of amines is very small, and hence they rapidly interconvert into one another by a process called nitrogen inversion or amine inversion. During this nitrogen inversion, the state of hybridization of N changes from sp3 to sp2, give a planar transition state in which in turn can either revert to the starting amine or its enantiomer as shown in figure 9.1. Look at the figure 9.1. Since the rate of this inversion is very high, therefore tertiary amines of the type R1, R2, R3 and through chiral exist as racemic mixtures which cannot be resolved. Optical activity of quaternary ammonium salts of the types R1, R2, R3, R4, NX. The lone pair of electrons on the N atom is involved in nitrogen inversion and hence racemization of tertiary amines with different substituents occurs. However, if the lone pair of electrons or nitrogen is bonded to four different substituents, then racemization due to nitrogen inversion will not be possible and hence such quaternary ammonium salt should exhibit optical activity. This prediction has been found to be true. For example, allyl benzyl methyl phenyl ammonium iodide has been resolved into two optically active forms shown in figure point 9.2. Look at this figure. Nomenclature of amines. Aliphatic amines in the common system. Aliphatic amines are named by the following two methods. According to one method, aliphatic amines are called alkyl amines. The common name of aliphatic primary amines are then obtained by adding the suffix amine to the name of the alkyl group attached to the nitrogen atom. In case of mixed secondary and tertiary amines, the names of the alkyl groups are arranged in alphabetical order and the suffix amine is then added. However, for simple secondary and tertiary amines respectively, the prefixes di and tri are used before the name of the alkyl group. Similarly, the names of era alkyl amines are derived by adding the suffix amine to the name of the era alkyl group or groups arranged in alphabetical order. According to the second system, aliphatic amines are called aminoalkenes in the system. The primary amines are named by adding the prefix amino to the name of the parent alkene corresponding to the longest possible straight chain. The position of the amino group and that of the substituents, if any, are indicated by the Arabic numerals with the carbon atom bearing the amino group getting the lowest possible number. Secondary and tertiary amines are named respectively as N-alkyl aminoalkanes and N-alkyl aminoalkanes or N-dialkyl aminoalkanes in case the two substituent alkyl groups are the same. The largest alkyl group forms a part of the aminoalkane while the smaller alkyl groups are considered as substituents. The prefixes N and N simply mean that the alkyl groups are attached to the nitrogen atom rather than to a carbon atom. In case of era alkyl amines, the position of the aryl group is indicated by a suitable number. In the IUPAC system, aliphatic amines are called alkane amines. These names are obtained by removing the final E from the name of the corresponding alkane and adding the suffix amine. It may be noted here that regardless of the system of nomenclature, the complete name of an amine is always written as one word. The common and IUPAC names of some aliphatic amines are given below. Look at this table. In case of mixed secondary and tertiary amines in which one of the alkyl groups has three or more carbon atoms and hence can exhibit position isomerism, the position of carbon atom of the chain to which the nitrogen is attached is included in the same name of the amine. For example, 2N-methyl amino 4-methyl pentane, N4-dimethyl pent 2 amine. In case of polyfunctional compounds, the amine is named as a derivative of the principal functional group. For example, 2-amino-ethanol, 4-aminobutanoic acid. If, however, all the functional groups are substituent functional groups, the compound is named as a derivative of the compound containing the functional group which comes first in the alphabetical order. For example, N-methyl 2-nitropentane amine. In case of unsaturated amines, the double triple bond is given the preference. For example, 1-propan amine, prop 1-ene 3 amine. Aromatic amines. In the common system, aromatic amines are called aryl amines. The name of an individual amine is then obtained by adding the suffix amine to the name of the aryl group. More often, they are named as derivatives of the simplest aromatic amine called aniline. However, in some cases, special names are also used. For example, orthometaparatoluidine for orthometapara methylaniline and orthometaparanicidine for orthomerapeta methoxyaniline. Even n-phenyl derivative of aniline is generally called diphenylamine. And the IUPAC system, the simplest aromatic amine is called benzeneamine, and the other amines are named as derivatives of this amine. It may be noted here again that the complete name of an amine is always written as one word. The common and IUPAC names of some aryl amines are given below. Since amines are better known by their common names, therefore in this unit we shall be using common names more frequently, though here and there some IUPAC names have also been given. Preparation of amines. Amines are generally prepared by the following methods. Reduction of nitro compounds. The nitro compounds can be easily reduced to the corresponding primary amines either by catalytic hydrogenation or by combination of an active metal and a mineral acid. This method is particularly useful for the preparation of aromatic primary amines, since aromatic nitro compounds can be easily prepared by nitration of arenes. In recent years, this method has become increasingly important even for the preparation of aliphatic primary amines, since aliphatic nitro compounds are now being prepared commercially by vapor phase nitration of alkanes, nitrobenzene to aniline. One disadvantage of catalytic hydrogenation is that other reducible groups such as ethylenic double bond, if present in the nitro compound, also gets reduced. For example, p-nitroserine, p-ethyl aniline. Reduction with an active metal such as ferrous, SN zinc, and concentrated hydrochloric acid. For example, reduction of nitrobenzene with SnHCl first gives a chlorostone salt from which free amine is recovered by the addition of alkali followed by steam distillation. Nitrobenzene to aniline. Lithium aluminium hydride can also be used for the reduction of aliphatic but not nitro compounds. Nitroethane to ethylamine. In case of di or tri-nitro compound, selective reduction of one nitro group can also be achieved by using ammonium hydrogen sulfide as a reducing agent. By the reduction of nitriles, aliphatic and ara-alkyl primary amines can be easily prepared by the reduction of the corresponding nitriles, either catalytically with H2 and nickel or chemically with lithium aluminium hydride or sodium and alcohol. Reduction with sodium and alcohol is called Mendeus reduction. Synthetic importance. Since ara-alkyl nitriles can be easily prepared by the action of alcoholic NaCN or KCN on the corresponding alkyl ara-alkyl halides, this gives us an excellent method for converting alkyl halides into primary amines having one carbon atom more than the parent alkyl halide. Thus, although aryl nitriles needed for the purpose cannot be prepared by the action of KCN on the corresponding aryl halides, yet they can be easily prepared by the action of aqueous KCN on the corresponding arene diazonium salts. Reductive amination. Primary, secondary, and tertiary amines can be prepared from aldehydes and ketones by reductive amination. It involves the treatment of an aldehyde or a ketone with ammonia or an amine in presence of a reducing agent. The reaction occurs through the intermediate formation of an amine, which upon reduction gives the corresponding amine. The reduction of the amine is achieved either catalytically with Rene at 373 Kelvin and 150 atmosphere pressure, or chemically with sodium cyanoborohydride. Sodium cyanoborohydride, being less reactive than NaBH4, reduces the amine but not the carbonyl compound. Primary amines are formed by treatment of an aldehyde or ketone with ammonia in presence of a reducing agent. Mechanism. Reductive amination occurs through intermediate formation of an amine and occurs through the following steps. Secondary amines are formed by treatment of an aldehyde or ketone with a primary amine in presence of a reducing agent. Similarly, tertiary amines are formed when an aldehyde or a ketone is treated with a secondary amine in presence of a reducing agent. Merits. It is particularly useful method for the preparation of primary amines containing a secondary alkyl group. Recall these amines are difficult to prepare by homophone ammonolysis of allyl halides because of the tendency of Sag alkyl halides to undergo elimination. Limitations. The primary amines formed during reductive amination can react further with the aldehyde or ketone to form a certain amount of the secondary amine. This can, however, be avoided by using desired proportions of the reactants. Gabriel phthalimide reaction. This is a very convenient method for the preparation of pure aliphatic and alkyl primary amines. Phthalide contains a imino group flanked by two electron withdrawing carbonyl groups, and hence the hydrogen of the imino group is acidic. Therefore, phthalimide can be easily converted into the potassium salt by treatment with an alcoholic solution of potassium hydroxide. Potassium phthalimide on heating with an alkyl or ara-alkyl halide gives the corresponding and substituted phthalimide. This upon hydrolysis with hot diluted HCl 20% under pressure or with boiling alkali gives primary amines. Phthalic acid can again be converted into phthalimide and used over and over again. Similarly, benzyl amine can be prepared by using benzyl chloride and glycine by using chloroacetic acid in phase of ethyl iodide in the above reaction. Hydrogenalysis of N-alkyl phthalimides is a more convenient and efficient method as compared to acidic basic hydrolysis for obtaining primary amines using Gabriel synthesis. For example, Hofmann degradation of primary amines. Hofmann bromide reaction. When a primary amide is treated with bromine or chlorine in aqueous alkali, it gives a primary amine containing one carbon atom less than the original amide. Mechanism. Br2 reacts with alkali to form hypobromite ion, which initiates the reaction. The reaction is believed to occur through the following steps. Evidence in support of the mechanism. This mechanism has been supported by the observation that N-bromoamide and alkyl isocyanates have actually been isolated as intermediates in the above reaction. These intermediates yield the expected amine when treated with KOH. Isocyanate as an intermediate in the above reaction is further supported by the observation that when the reaction is carried out with methanolic instead of aqueous NaOH, a methyl carbonate or ureethane is obtained instead of the amine. For example, methylamine acetamide, methyl and methyl carbamate. The methyl and methyl carbamate is actually formed by addition of CH3OH2 methyl isocyanate formed as an intermediate in the above reaction. Stereochemistry. Although in the above mechanism it has been shown that step 3 involving the loss of Br to form acyl nitrine and step 4 involving the rearrangement of group R from carbon to electron deficient N atom occur separately, no evidence is yet available to suggest the formation of acyl nitrines as intermediates in these reactions. Therefore, it is suggested that both these steps occur simultaneously as depicted below. In other words, Hofmann bromomide is an intermolecular rearrangement in which the migrating group shifts from carbon to nitrogen with retention of configuration. This is supported by the observation that optically active amide gives optically active amine with retention of configuration. Separation of primary, secondary, and tertiary amines. Certain methods of preparation of amines such as ammonolysis of alkyl halides gives a mixture of primary, secondary and tertiary amines and quaternary ammonium salts. In order to separate such a mixture into individual components, it is first distilled with KOH when quaternary ammonium salt being non-volatile remains behind while the mixture of amine distills over. The mixture of amines thus obtained is then separated by the following methods. Fractional distillation. A mixture of primary, secondary, and tertiary amines can be separated into individual components by fractional distillation since their boiling points are fairly apart. For example, primary amine, secondary amine, tertiary amine. This is the most satisfactory method and is now used industrially because of the availability of highly efficient fractionating columns which can separate a mixture of amines even if their boiling are quite close. Heisenberg method reaction with benzene sulfonyl chloride. This is an excellent method for the separating a mixture of primary, secondary and tertiary amines. In this method, a mixture of primary, secondary and tertiary amines is treated with benzene sulfonyl chloride and the resulting reaction mixture is basified with aqueous KOH solution when the three amines react differently as discussed below. A primary amine forms an alkyl benzene sulfonamide which because of the presence of an acidic hydrogen on the N atom dissolves in KOH. A secondary amine forms an anti-alkyl benzene sulfonamide which due to the absence of acidic hydrogen on N atom does not dissolve in KOH. The tertiary amine under these conditions does not react at all since it does not contain a replaceable hydrogen on the nitrogen atom. The reaction mixture obtained after treatment with benzene sulfonyl chloride in presence of alkali is distilled with tertiary amine distills over the remaining mixture is filtered and the filtrate on acidification gives the sulfonyl amount of primary amine while the solid residue left on the filter paper in the sulfonamide of secondary amines. The two sulfonamides thus isolated are hydrolyzed separately either by refluxing with 70% H2SO4 or 25% KHCl to form the corresponding amine hydrochlorides from which the amines are regenerated on treatment with NaOH solution. Recently, benzene sulfonyl chloride is replaced by p-toluene sulfonyl chloride, tosyl chloride since the substituted sulfonamide thus formed a stable solid which can be easily purified by crystallization. Unfortunately, the Heisenberg method is not suitable for higher primary amines and heptylamine because their sulfonamides are insoluble in alkali. Hoffman method reaction with diethyl oxalate. In this method, a mixture of primary, secondary, and tertiary amine is treated with diethyl oxalate when the three amines react differently as discussed below. The primary amine forms the corresponding substituted oxamide which is usually a crystalline. The secondary amine forms a diethyl oxamic ester which is generally a liquid. The tertiary amine under these conditions does not react at all since it does not contain a replaceable hydrogen atom. The reaction mixture containing the substituted oxamide, oxamic ester, and unreacted tertiary amine is distilled when the nitri tertiary amines distills over the residual mixture containing the substituted oxamide solid and the oxamic ester liquid is separated by the simple filtration. Both the oxamide and the oxamic ester, when both boiled separately with a strong base, regenerate the corresponding amines thus. Physical properties of amines. Some important physical properties of amines are discussed below. Color and odor. Pure amines are almost colorless but develop color on keeping in air for a long time. This is due to the reason that amines, especially aromatic amines, are readily oxidized in air to form colored oxidation product. Lower aliphatic amines are gases and smell very much like ammonia, but the higher amines are liquids with fishy odors. Lower aromatic amines are liquids having characteristic unpleasant odors, but the higher ones are low melting solids which are almost odorless. Aromatic amines in general are toxic. Boiling points. Amines have higher boiling point than hydrocarbons of comparable molecular masses. This is due to the reason that amines being polar from intermolecular H bonds expect tertiary. Amines which do not have hydrogen atoms linked to the nitrogen atom as shown below and thus exist as associated molecules. The degree of association, however, depends upon the extent of H bonding since primary amines have two secondary amines and while tertiary amines have no hydrogen linked to nitrogen. Therefore, among isomeric amines, primary amines have the highest while tertiary amines have the lowest boiling point. Since the electronegativity of nitrogen is lower than the of oxygen, therefore amines form weaker H bonds as compared to alcohols and carboxylic acids. As a result, amines are not associated to the extent of alcohols and carboxylic acids, and hence the boiling points of amines are lower than those of alcohols and carboxylic acids of comparable molecular masses. For example, ethylamine boils at 292 Kelvin while ethyl alcohol and formic acid. Solubility. All the three classes of aliphatic amines, primary, secondary, and tertiary, form H bonds with water. As a result, lower aliphatic amines are soluble in water. Methylamine and ethylamine are gases, but they are highly insoluble in water. That is why they are sold in the market as their 30%, 34% aqueous solution. However, as the size of the alkyl group increases with increase in the molecular mass, the solubility decreases due to the corresponding increase in the hydrocarbon part of the molecule. The borderline solubility is reached with amines of about 6 carbon atoms in the molecule. However, amines are quite soluble in organic solvents such as benzene, ether, alcohol, etc. Aromatic amines, on the other hand, are insoluble in water. This is due to the larger hydrocarbon part, which tends to retard the formation of H bond. Thus, aniline is almost insoluble in water. However, it is quite soluble in benzene, ether, alcohol, etc. Basicity. Basicity of amines. Like ammonia, all the three classes of amines contain a pair of unshared electrons on the nitrogen atom. Therefore, they have a strong tendency to donate this electron pair to proton or any other electron deficient species. As a result, all the three classes of amines like ammonia are basic in nature. The basicity of an amine can be easily expressed either in terms of its basicity constant value. Basicity constant. When an amine is dissolved or suspended in water, the following equilibrium is established. The equilibrium constant for this reaction is, since water is present in larger excess, its concentration is taken to be constant. Rewriting the above expression, we have this new equilibrium constant Kb, which gives a measure of the extent to which an amine expects a proton. Water is called basicity constant. In other words, Kb is the index of the basicity of an amine. The greater the numeral value of Kb, the stronger is the amine. Pkb value, since the value of Kb vary by many orders of magnitude, it is more convenient to express the basicity of an amine in terms of its pKb value, negative logarithm of Kb. Evidently, smaller the numerical value of pKb, more basic is the amine. The Kb and pKb values of some amines are given in table 9.1. Structure basicity relationship of amines. All classes of aliphatic amines are stronger bases than ammonia. Aromatic amines are much weaker bases than ammonia. Mixed secondary and tertiary amines are slightly more basic than purely aromatic amines. For example, N-methylaniline are stronger bases than aniline or diphenylamine. Let us now discuss the effect of structure on the basicity of aliphatic and aromatic amines. Basicity of aliphatic amines. As stated above, all the three classes of aliphatic amines are stronger bases than ammonia. This is due to the reason that alkyl groups are electron donating groups. As a result, the electron density on the nitrogen atom increases, and thus they can donate the lone pair of electrons more easily than ammonia. The basicity of amines should decrease in the order tertiary, secondary, primary, ammonia. It has been found that in aqueous solution, secondary amines are invariably found to be stronger because the primary amines, while tertiary amines are found to be weaker bases than secondary amines, and sometimes even weaker primary amines. The actual basicity order of the methyl and ethylene is an unknown. This is the reason why the actual order is different from the expected order. The basicity of an amine in aqueous solution primarily depends upon the stability of the ammonia cation or the conjugate acid formed by accepting a proton from water. The stability of the ammonium cation in turn depends upon a combination of the following three factors: I effect of the alkyl groups, extent of H bonding with water molecules, steric effects of the alkyl groups. Let us now discuss these factors one by one. As the number of alkyl groups increases, the dispersal of positive charge on the ammonium cation by the I effect of the alkyl group increases. Accordingly, thus on the basis of I effect alone, the basicity of amine should decrease in the order tertiary, primary, secondary, primary. The stability of the ammonia cation due to the H bonding depends upon the number of H atom present on the N atom. Obviously, greater the number of H atom on N atom, more stable is the ammonium cation. Thus, the ammonium cation derived from a primary amine is the most stable since it has 3 H atoms which can form H bond with H2O. The ammonium cation derived from the secondary amine is less stable since it has 2 H atoms, while that of the tertiary amine is at the least stable since it has only one H atom which can form H bond with H2O as shown below. However, in case of ammonium cation derived from tertiary amines, there is some steric repulsion to H bonding and hence stability further decreases. Thus, on the basis of H bonding and steric factors, the basicity of amine should decrease in the order primary, secondary, and tertiary. From the above discussion, we may conclude that if a combination of I effect on the alkyl groups, H bonding, and factors, steric factors all these All these three factors are favorable for secondary amines, and hence secondary amines are the strongest bases. If the alkyl group is small CH3, then there is no steric hindrance to H bonding. In other words, the stability due to the hydrogen bonding predominates over the stability due to plus I effect the CH3 group, and hence primary amine CH3NH2 is a stronger base than tertiary amine. In other words, the overall decreasing strength of methylamines is, look at this, if however the alkyl group is bigger than CH3 group, ethyl, propyl, etc., there will be some steric hindrance to H bonding. As a result, stability due to plus I effect predominates over the stability due to H bonding, and hence three tertiary amines become more basic than primary amines. In other words, the overall decreasing strength of ethylamines follows the sequence. It is interesting to note that in gas phase or in non-aqueous solvents such as chlorobenzene, etc., the the solvation effects, the stabilization of conjugate acid due to H bonding are absent, and hence in these media the basicity of amines depends only on the plus I effect of the alkyl group. Thus, the basicity of primary, secondary, and tertiary amines is the gas phase or in non-aqueous solvent following the order. Tertiary amines, secondary amines, and primary amines are NH3. Basicity of ara-alkyl amines. Ara-alkyl amines are essentially aryl substituted alkyl amines due to the electron withdrawing inductive effect or minus I effect of the aryl group. The unshared electron pair of nitrogen in these amines is less easily available than in alkyl amines for sharing with the proton. As a result, simple ara-alkyl amines are weaker bases than alkyl amines, for example. Further, as the distance between the aryl groups and the amino group increases, the minus I effect decreases and hence the basicity increases accordingly. For example, basicity of aromatic amines. Aromatic amines are far less basic than ammonia and aliphatic amines. This may be explained as follows. Due to resonance in aniline, aniline may be regarded as a resonance hybrid of the following structures. As a result of resonance, the lone pair of electrons on the nitrogen atom get delocalized over the benzene ring, and this is easily available for protonation. Therefore, aromatic amines are weaker bases than ammonia. Lower stability of anilinium ion than aniline. If we compare the relative stabilities of aniline and the anilinium ion, which aniline forms by accepting a proton, we find that whereas aniline is a resonance hybrid of 5 structures, anilinium ion is a resonance hybrid of only 2 structures. Structures analogues to third, fourth, and were not possible in this case due to localization of the lone pair of electrons on nitrogen because of the formation of an additional nitrogen-hydrogen bond. In other words, aniline is more stable than anilinium ion, hence aniline has very little tendency to combine with the proton to form anilinium ion. On the other hand, in case of ammonium and aliphatic amines, delocalization of the lone pair of electrons on the nitrogen atom by resonance is not possible. Furthermore, the electron density on the nitrogen atom is increased by electron donating inductive effect of the alkyl group. As a result, ammonium and aliphatic amines are much stronger bases than aniline and other aromatic amines. Effect of substituents on the basicity of aromatic amines. Let us now discuss the effect of substituents on the basicity of aromatic amines. Effect of substituents on the nitrogen atom. When the hydrogen atom of the amino group in primary aryl amines are replaced by electron donating alkyl groups, the basicity of the resultant aryl amine increases. For example, N-methylaniline and N-dimethylaniline are stronger bases than aniline. Conversely, if the hydrogen atom of the amino group are replaced by electron withdrawing groups, the basicity decreases. For example, diphenylamine is a much weaker base than aniline, and triphenylamine is too weak a base to measure its pKb. Effect of nuclear substituents on the basicity of aryl amines. Basicities of some substituted anilines, pKb for anilines. From the above table, following points emerge. Electron donating substituent tend to increase and electron withdrawing substituent tend to decrease the basicity of anilines and aryl amines. The base weakening effect of the electron withdrawing and substituent and base strengthening effect of the electron donating substituents is more marked at para position than at meta position. Ortho-substituted anilines are usually weaker bases than aniline regardless of the nature, electron donating or electron withdrawing of the substituent. This is called ortho effect and is probably due to a combination of steric and electronic factors. Explanation: electron donating substituents tend to increase the electron density on the nitrogen atom. As a result, the lone pair of electrons on the nitrogen atom is more easily available for protonation. At the same time, electron donating substituent tends to disperse the positive charge of the substituted anilinium ion and thus increase their stability relative to the parent amines. The combined effect is that electron donating substituents increase the basicity of aromatic amines relative to the parent amine. The base strengthening effect of the electron donating substituent is more pronounced at para position than at meta position. For example, para anisidine is more basic than meta anisidine. The reason being that in para anisidine, one of the resonance structures carries the negative charge on the carbon to which the amino group is attached. This structure directly increases the electron density on the nitrogen atom, but no such resonance structure is possible for meta anisidine. Resonance structure of meta-anisidine. In other words, para-methoxy group increases the electron density more on the nitrogen atom than the meta-methoxy group. Therefore, para-anisidine is a stronger base than meta-anisidine. It may be noted here that groups like OH, O, CH3, OH, etc. have both electron withdrawing inductive effect and electron donating resonance when such a group at present para position outweighs the I minus I effect and thus the overall effect is electron donating. As a result, para methoxyaniline is a stronger base than aniline. However, when OCH3 group is present at a meta position, it can exert only minus I effect since resonance effect does not operate at meta position. This decreases the electron density on nitrogen atom and hence meta methoxyaniline is a weaker base than aniline. Conversely, the electron withdrawing substituents tend to decrease the electron density on the nitrogen atom. As a result, the lone pair of electrons on the nitrogen atom becomes less easily available for protonation and the basicity decreases. At the same time, electron withdrawing substituents tend to intensify the positive charge of the substituted anilinium ion and thus decrease their stability relative to the parent amines. The combined effect is that electron withdrawing substituent decrease the basicity of aromatic amines relative to the parent amines. Here again, the base weakening effect of the electron withdrawing substituents is more marked at para position than meta position. For example, para nitroaniline is a weaker base than meta nitroaniline. The reason being that in para nitroaniline, one of the resonating structures carries the negative charge on the carbon to which NO2 group is attached. This structure directly decreases the electron density of the nitrogen atom by punishing the electron from the NH2 group to the NO2 group. But no such resonance form is possible for the meta-nitroaniline. In other words, para-nitro group decreases the electron density on nitrogen more than the meta-nitro group. Therefore, para-nitroaniline is a weaker base than a meta-nitroaniline. In the light of the above discussion, basicity of ortho, meta and para-toluidines relative to aniline decreases in the order. Similarly, the basicity of ortho, meta and para-nitroanilines relative to aniline decreases in the order. Steric effects. Since a proton occupies a very small volume, therefore steric effects do not have any significant effect on the proton transfer reactions. However, steric effects may indirectly affect the base strength by interfering in resonance stabilization. Since for resonance to occur, it is essential that all the atoms must lie in a plane. Therefore, any factor which prevents atoms from assuming coplanarity reduces resonance and thus influences the availability of the electron on the nitrogen atom. Consequently, resonance is prevented and hence lone pair of electrons on N in amine is not contributed towards the benzene ring to the same extent as in amine. Therefore, the lone pair of electron on N in amine is more easily available for protonation than in amine and hence amine is a stronger base than amine primary. On similar lines, we can explain that N-dimethyl pyramide is a stronger base than pyramide third. Chemical properties of amines. The chemical properties of amines largely depend upon the pressure of the lone pairs of electrons on the nitrogen atom. Some important physical chemical properties of amines are discussed below. Basic character. As discussed above, all the three classes of amines, because of the presence of a lone pair of electron on the nitrogen atom, behave as bases. Their basic character is shown by the following reaction. Reaction with water. Due to the presence of a lone pair of electron on the N atom, amines like NH3 are stronger bases than H2O. Therefore, they react with water to form alkyl or aryl ammonium hydroxide, which ionizes to furnish hydroxyl ions. Due to the formation of hydroxide ion, the aqueous solution of amines are basic in nature. The presence of the hydroxide ion in the aqueous solution of amines is detected by the precipitation of metal hydroxides such as aluminium hydroxide or ferric hydroxide. Reaction with acids. Being basic, all types of amines react with mineral acids such as HCl, HNO3, H2SO4 to form soluble salts. These amine salts are ionic compounds. They are soluble in water but are insoluble in non-polar solvents such as benzene, chloroform, etc. In contrast, higher amines are generally insoluble in water but are soluble in organic solvent. This difference in solubility behavior of amines and their salt is often used to detect amines and separately them from non-basic compounds. Further, amines react with chloroplatinic acid to form insoluble salts called chloroplatinates. Reaction with meta-ions like ammonium amines also form soluble coordination complexes with transition metal ions such as AgCu ions, etc. Thus, silver chloride dissolves in methyl amine solution due to formation of a soluble complex salt shown as below. Similarly, like ammonia, amines such as methylamine, ethylamine react with Cu ion to form a deep blue solution to the formation of following soluble coordination complex. Alkylation. Both aliphatic and aromatic primary, secondary, and tertiary amines react with alkyl halides to form secondary and tertiary amines and quaternary ammonium salt respectively. This process of introducing an alkyl group into any molecule is called alkylation. The process of converting an amine into its quaternary ammonium salt on treatment with excess of an alkyl halide is called exohertic alkylation. If the alkyl halide used in methyl iodide, the process is commonly known as exohertic methylation. Acylation. Reaction with acid chlorides and acid anhydrides. Primary and secondary amines but not tertiary amines because they do not contain a H atom on the N atom and undergo nucleophilic acylation reactions when treated with acid chlorides or acid anhydrides to form N substituted amide thus. Unlike alkylation reactions of amines, the amides formed here do not react further with acid chlorides and hydrides because the amide is non-basic and a poor nucleophile due to delocalization of its lone pair of electrons on the carbonyl group thus. Acylation with aliphatic acid chlorides and anhydride is usually carried out in presence of pyridine. However, with aromatic acid chlorides, acylation is usually carried out in presence of aqueous NaOH solution. This reaction is called Schotten-Bowman reaction. The process of acylation is often used for identification of aliphatic and aromatic primary and secondary amines. This is because acyl derivatives, particularly acetyl or benzoyl derivatives of these amines, are generally crystalline solids having sharp melting boiling points. Reaction with nitrous acid. Primary, secondary, and tertiary amine react differently with nitrous acid. Since nitrous acid is unstable, it is prepared in situ by the action of dilute hydrochloric acid on sodium nitrate. Primary amines. Aromatic primary amines react with nitrous acid at 273 Kelvin to 278 Kelvin to form arene diazonium salt. The reaction of converting aromatic primary amine into diazonium salt by treatment with a cold aqueous solution nitrous acid is called desertization. Primary aliphatic amines also react with cold nitrous acid to yield diazonium salt, but aliphatic diazonium salt are unstable even in the cold and decompose as soon as they are formed to give a complex mixture consisting of alcohol, alkenes, alkyl halides with the quantitative evolution of N2 gas. Secondary amines. Both aliphatic and aromatic secondary amines react with nitrous acid to give N-nitrosoamines which being insoluble in dilute mineral acids separate out as yellow oily compounds. These N-nitrosoamines on warming with a crystal of phenol and a few drops of concentrated H2SO form a green solution which when made alkaline with aqueous NaOH turn deep blue and then red on dilution. This reaction is called Lieberman-nitroso reaction. Aromatic tertiary amines undergo electrophilic substitution with nitrosoaminium ion at para position of the phenyl ring to the form green colored para-nitrosamines, for example. Mechanism: protonation of nitrous acid followed by loss of water generates nitrosonium ion, which acts like the benzene ring at the less hindered para position to afford the product as shown below. It may be emphasized here that as compared to electrophilic species involved in halogenation, nitration, sulfonation, etc., nitrosonium ion is a very weak electrophile and thus react only with aromatic compounds containing strongly activating groups such as dialkyl amino and hydroxy groups. Aliphatic tertiary amines, on the other hand, react with nitrous acid to form water-soluble nitrite salts. Sometimes these amine salts decompose to yield an nitroso derivative of the secondary amine along with an aldehyde or a ketone. Thus, it is evident from the above discussion that the reaction with nitrous acid can be used for the distinction of primary, secondary, and tertiary amine, and in some cases, it is also possible to determine whether the amine is aliphatic or aromatic. Carbyl amine reaction or isocyanide test. Both aliphatic and aromatic primary amines, when warmed with chloroform and an alcoholic solution of KOH, produce isocyanides or carbyl amines which have very pleasant odors. In contrast, secondary and tertiary amines, both aliphatic and aromatic, do not give the test. Therefore, this test is used to distinguish primary amines from secondary and tertiary amines. This reaction is believed to occur through intermediate formation of dichlorocarbene as shown below. This reaction is believed to occur through nucleophilic attack on C double bond S followed by loss. With aromatic amines, aromatic primary amines, however, react in a slightly different manner. For example, when aniline is heated with ethanoloic and solid KOH, it gives an N-diphenylthiourea, which upon treatment with concentrated HCl gives phenyl isothiocyanate. Reaction with aldehydes and ketones. Primary amines, both aliphatic and aromatic, react with aldehyde and ketone in presence of a trace of an acid as catalyst to produce azomethanenes called Schiff bases or anilines. Secondary amines also react with aldehydes and ketones containing alpha hydrogen atom to form first carbonyl amines, which being unstable readily lose a molecule of H2O to form stable amines, thus acidic nature. Although amines are essentially basic in nature, primary and secondary amines but not tertiary amines, since they do not have hydrogen atom or a nitrogen atom, can also act as a weak acid when treated with strong bases such as sodium, metal, and butyl lithium, etc. LDA is an extremely powerful base. It dissolves in organic salts such as THF. It is also too hindered to add to the carbonyl group in nucleophilic addition reaction, but is nevertheless extremely reactive even at 199 Kelvin. Primary and secondary amines, but not tertiary amine, because they do not contain a hydrogen on the nitrogen atom, also react with Grignard reagent strong bases to form alkanes corresponding to the alkyl group of the Grignard reagent. Oxidation of amines give different products depending upon the nature of amine and the oxidizing agent. The oxidizing agents, which are commonly used as H2O2, peroxy acids, Carose acid, primary aliphatic amines undergo oxidation to nitro compounds through a sequence of reactions. Primary amine, hydroxyl amine, nitroso compound, nitro compound. Primary amines in which the ONH2 group is attached to a tertiary carbon can be oxidized with KMnO4 to the corresponding nitro compounds in excellent yield. Secondary aliphatic amines on oxidation with KMnO4 give tetraalkyl hydrazenes. With Carose acid or H2O2, secondary aliphatic amines, however, give the corresponding N-hydroxyl amines. Tertiary aliphatic amines are not oxidized by KMnO4 but are oxidized to the corresponding amine N oxides by Carose acid, ozone, or H2O2. Aromatic amines, on the other hand, because of the presence of high electron density on the benzene ring, are easily oxidized on exposure to air or oxidizing agent, leading to the formation of complex colored products. For example, electrophilic substitution reaction. In addition to the reaction of amino group, aromatic amines also undergo typical electrophilic substitution reactions of the aromatic ring. In all these reactions, the NH2 or NHR or NR2 group strongly activates the aromatic ring through delocalization of the lone pair of electrons of the N atom over the aromatic ring referred to structures. Due to the strong activating effect of the NH2 group, Aromatic amines undergo electrophilic substitution reaction rarely, and it is difficult to stop the reaction to the mono substitution stage. Some typical electrophilic substitution reactions of aromatic amines are discussed below. Halogenation. Due to the strong activating effect of the amino group, halogenation of amines occur fast, and the halogen enters the para and both the ortho position even in the absence of a catalyst. For example, aniline or treatment with bromine water gives 2,4,6 tribromoaniline. If however a monohalogenated derivative is required, the amino group is first acetylated and the halogenation of the ring is carried out. After halogenation, the acetyl group is removed by the hydrolysis and the monohalogenated amine is obtained. Nitric acid is not only a nitrating agent but also acts as a strong oxidizing agent. Da- as a result, direct nitration of aromatic amines is not a useful reaction since it often gives terry oxidation product along with some nitration product. However, under controlled conditions, nitration of anilines gives a mixture of para-nitroaniline and meta-nitroaniline in approx 1:1. This reaction this reason for formation of larger amount of unexpected meta-nitrosoaniline is that under strongly acidic conditions of nitration, most of the aniline is converted into anilinium ion, and since NH3 is an meta-directing group, therefore is an expectedly large amount of meta-nitroaniline is obtained. Therefore, to avoid these problems, the most convenient method to carry out the nitration of aniline is give the first product to amino group by acetylation. The acetyl group is finally removed by the hydrolysis to give a mixture of ortho and para-nitroanilines. Sulfonation. In spite of the presence of activating amino groups, sulfonation of aromatic amines occur only under drastic conditions. For example, when aniline is treated with concentrated H2SO4, it gives para-aminobenzene sulfonic acid called sulfonilic acid. This reaction is believed to occur through the amine salt as depicted below. Sulfonilic acid contains both an acidic as well as basic. It is therefore quite unstable. Then sulfonilic acid exists as an internal salt. During the formation of this salt, the NH2 group has expected the proton donated by SO3H group. Such type of internal salt are called dipolar or zwitterions. Due to zwitterion character, sulfonilic acid has high melting point and is particularly insoluble in water and organic salts. Sulfonilic acid is an important intermediate in the manufacture of dyes and drugs. Sulfonilic acid and its derivatives are also used in the manufacture of well-known sulfur drugs such as sulfenthiazole, sulfadiazine, sulfapyridines, etc., which are widely used agent bacterial infections. Distinction between primary, secondary, and tertiary amines. Reaction with nitrous acid. Aliphatic primary amines react with cold HNO2 and 2H3 to form alcohol with the evolution of N2 gas. Aromatic primary amines, on the other hand, react with HNO2 at 273 to 278 Kelvin to form diazonium salt, which upon treatment with an alkaline solution of 2-naphthalol or beta-naphthol from orange or red color azodize. Test is called azodide test and is used to distinguish aromatic primary amines from aliphatic primary amines. The chemistry of the test is described below. Secondary amines. Both aliphatic or aromatic react with HNO to form N-nitrosoamines, which are yellow oily compound. These N-nitrosoamines, on warming with a crystal of phenol and few drops of H2SO4, form a green solution, which when made alkaline with aqueous NaOH turn deep blue and then red on dilution. This reaction is Lieberman nitrosoamine reaction and is used to distinguish secondary from primary and tertiary amines. Tertiary amines react with HNO2 at 273 to 278 Kelvin to form soluble amines nitrites, which decompose and heating to give N-nitrosoamines and other products. Therefore, this reaction is used for distinguish of tertiary amines from primary and secondary amines. Heisenberg test. This is an excellent test for distinguish primary, secondary, and tertiary amines. In this test, the amine is shaken the benzene sulfonyl chloride in the presence of excess of aqueous KOH solution. When a primary amine gives a clear solution, when acidification gives an insoluble N-alkyl benzene sulfonoamide, a secondary amine gives an N-dialkyl benzene sulfonoamide which remains unaffected on addition of acid. A tertiary amine does not react at all, therefore it remains insoluble in the alkaline solution but dissolves on acidification to give a clear solution. For chemistry of these reactions, refer to for separation of primary, secondary and tertiary amines, carbolamine test or isocyanide test. Both aliphatic and aromatic primary amines on heating with CHCl3 in presence of alcoholic KOH form isocyanides on carbylamines having extremely unpleasant odors. This reaction is called carbylamine reaction and is used to distinguish primary amines from secondary and tertiary amines. Amine salt as phase transfer catalysts. Tetraalkyl ammonium salt or quaternary ammonium salt as they are commonly have been called widely used as catalysts for many different types of organic reaction. Let us consider as SN2 reaction. Between 1 bromo-octane and sodium cyanide to form nanonitrile, suppose we dissolve 1 bromo-octane in benzene and stir the solution with an aqueous solution of NaCN. Since the organic layer and the water layer are immiscible, therefore cyanide ion present in the aqueous layer cannot come in contact with 1 bromo-octane present in the organic layer. Thus, there is no reaction. If, however, we add a small amount of quantity ammonium salt to this two-phase mixture and the mixture stirred non-nitrile is obtained in 92% yield in about 2 hours. How does quantity ammonium salt exert its catalytic effect? Let us now answer this question. Quantity ammonium salt is an ionic compound, therefore it is soluble in water. At the same time, due to presence of 4 hydrocarbon substituents on nitrogen, it is also soluble in organic solvents. When the positively charged quantity ammonium ion goes into the organic layer, a negatively charged counter ion must move into the organic layer to preserve electrical neutrality. Since the cyanide ion is present in much greater amount than the halide ion in the aqueous layer, therefore it is cyanide ion which gets transferred to organic layer. Now, due to the presence of 1 bromo-octane and cyanide ion in the same phase, a rapid reaction occurs and nanonitrile is formed and the halide ion is liberated. The halide ion is then transferred to the aqueous layer where it again reacts with NaCN to QCN and the reaction gets repeated over and over again. Thus, only a small amount of quantity ammonium salt is required, and this explanation is catalytic effect. Look at this figure 9.3. Illustration of phase transfer catalysis. Transfer of the inorganic ion in the presence from one phase to another is called phase transfer, and the quantity ammonium salt is called phase transfer catalyst. Apart from SN2 reaction, many other different kinds of organic reaction including alkylation of carbonyl compound, oxidation, reduction, etc. are now being carried out using phase transfer catalyst. In all these cases, the yields obtained are much better than when these reactions were carried out by other methods without using phase transfer catalysts. The most commonly used phase transfer catalysts are tetrabutyl ammonium chloride or benzyl triethyl ammonium chloride.